Here comes the most challenging chapter for this semester.
Oh boy.
Oh yay! We're going to be talking about reactions in aqueous solution. Some of the material you will have seen from honors, but we're going to take it to a whole new level. We're going to work through it slowly so that you have a solid understanding. This is going to fit into Big Idea 3, which is on your board. Couple terms we want to review, few formulas to review, and then we'll get into the new stuff. You know that when you dissolve one substance in another, if it dissolves, then you have a solution or a homogeneous mixture. And you know the solute gets dissolved, and the solvent does the dissolving. You can show the relationship between solute and solvent, or solute and solution, with concentration. And there are a lot of different ways to show concentration. The way we abbreviate concentration is with brackets. For example, if I wanted to know the concentration of sodium chloride, I would put it in brackets. And let's say, for example, the concentration is 2 molar. Molar is one way to represent concentration. And you know from last year in our previous chapter that molarity is moles of solute over the total volume of solution in liters. You also can do this in terms of millimoles, which really comes in handy when you have small volumes, because you can do millimoles of solute over the total volume of solution in milliliters. The milli would cancel, you get the same thing. So that's molarity. And that's primarily the way we're going to express concentration. In AP, we don't do molality because we took out colligative properties, so we're not going to play with molality this year. We do use mole fraction in the gas law chapter. So mole fraction, abbreviated X, is going to be moles of solute over moles of solution, where moles of solution is moles of solute plus moles of solvent. And then another one you can do is percent comp, where in solution chemistry, if you will, you're going to have the mass of the solute in grams over 100 grams of solution. So if your solute has a mass of 40 grams, what's the mass of the solvent? 60. So very straightforward. And the dilute versus concentrated issue would be something such as this. Of the two sodium chloride solutions, which one is more dilute? The second one. You have less or a smaller amount of moles per the same volume there. All right? So those terms should, for the most part, be review. You may see a little bit of this, not terribly much. All right, in terms of electrical properties of aqueous solutions, some aqueous solutions have the ability to conduct electricity. And when they do conduct electricity, we say that you have an electrolyte. Before we go into that, let's just go over some basic parts. Your electrical conductors or electrodes are just wires or metal plates, and that's shown here and here. Those are the wires or metal plates. and they'll be partially immersed in some type of solution, and they will be connected to a source of electricity. And what you can test here is whether the light bulb illuminates from the solution in question, and we'll take a look at that. Some of the other terms are listed here. Anode and cathode are your electrodes. One's positive, one's negative. You don't actually have to know which is which anymore. What carries the electricity through solution is the ion, and you know that anions are negatively charged, like a sulfide ion, S2 minus, or a cation such as calcium 2 plus. We'll talk more about the whole type of circuit later in the year, but what you will see here is that some substances can conduct electricity because they will dissociate into ions, and these ions will move freely, and as a result you'll get electricity. And a solute that makes enough ions for a solution to conduct electricity is referred to as an electrolyte, and we'll give you some examples of that. I'm going to show you how you can test conductivity. This guy's a little bit goofy, but he does run through several different solutions, so I think it's very helpful. What's going to happen here is you're going to have 1 molar solutions, and you're going to test whether each conducts electricity.
You click to the end. You accidentally click the end.
Well, that's because I'm a ding-dong.
You just click to the end.
Well, I'll eventually get it right.
Go back.
Maybe.
Back.
Yeah.
All right, let's get rid of that.
Oh my god.
Well, is that part of my problem?
Go back to, yeah.
I can do it. Here we go.
There you go.
Every time he wants to watch new videos and
Oh,
stuff.
hi. Today we're going to learn about solutions and how they
He's goofy.
Oh my goodness.
But he does test some goodies.
This is music.
So here's tap water. A little bit of conductivity.
distilled water.
Not even a little bit.
What?
All right, so tap water, yes. Distilled water, no. How come?
There's sediments in tap water that are removed in distilled water.
What are they?
Iron.
Starts with an I. Just ions.
Oh.
There are ions in tap water. That's why we don't make solutions with tap water.
Salt water, 1 teaspoon per cup. Hydrochloric acid. Nice. Sodium hydroxide. Just as concentrated. Sugar water. Sweet. Vinegar, oleic acid. Ethanol, a dissociative that doesn't dissociate. Don't try this at home. Barium sulfate. It's insoluble. No conductivity here.
What the heck?
All right, well, let's go through. He did test a lot of solutions. That's how we typically do it in the lab. Like methanol, we write MEOH, but I'll give you the chemical formulas here. So what he tested, I've got listed, and we'll go through all the ins and outs of this. So in regard to salt, such as sodium chloride is an ionic compound. It generates sodium ion and chloride ion. And This was a strong. We'll give it a smiley. And so that would be a strong electrolyte. Hydrochloric acid, that's a strong acid. It ionizes completely. Strong electrolyte, good conductor of electricity. Sodium hydroxide is a strong base. It ionizes completely. Strong electrolyte. Now sugar could be anything. I'm guessing it's glucose. Although he could have used sucrose, he didn't specify. And this does not ionize. And this is a non-electrolyte and doesn't conduct electricity. Vinegar is acetic acid. That's a weak conductor. And that's a weak electrolyte. Ethanol is CH3CH2OH, and that does not conduct electricity. Now, barium sulfate is ionic, but this is an insoluble salt or a barely soluble salt, and this too was a non-conductor. And we'll go through the solubility rules in a bit. And basically with my little chart, that's all the writing that's indicated there. It's just cuter. Oh, let me do this piece right here. Vinegar is a weak acid. Equilibrium lies far to the left, and so it does not ionize completely. You have far more molecular than you do ions, and as a result, it's just a weak conductor. You do have some ions. Huh? Okay. Nope. Better go buy some. I bought lighters.
About what?
Lighters. To light things on fire.
Corduroy.
Huh?
On the chart for barium sulfite, you put that it was a weak acid.
Awesome.
No, that should be a sad face. Thank you. Fix my sad face. It's sulfate. Barium sulfate.
Do we need to know that?
You need to know that most ionic compounds are strong electrolytes. You need to know strong acids and strong bases are strong electrolytes.
Okay.
That'll about do it. Alrighty. So everything I just said is written here, so we won't reread it. It should be worth it. And the rules for classifying are basically what I said. Typically, your ionic compounds are strong electrolytes. That's going to make them good conductors of electricity. A few monomolecular compounds, mainly the strong acids, are strong electrolytes. Most molecular compounds are either non-electrolytes or weak, and most organic compounds are typically weak, like your Cu groups as well as your amines. Okay? Not much there. We want to be able to calculate ions in solution, and we touched upon this in the previous chapter, but we're going to make it a little more complicated here. Not anything that's going to be tricky for you.
Would alkanes be electrolyte or not?
No, molecular. So, what you want to do is when you're testing whether a salt will conduct electricity, you're looking to see whether it will dissociate into ions. Sodium chloride as a solid, when dissolved in water, generates sodium ion and chloride ion. This equation is balanced: one sodium, one chlorine atom, one chlorine, balanced. The I, or the ions released, is the sum of the coefficient of the ions. That is the sum of the coefficients of products. So 1 plus 1 is 2. If you had calcium chloride, you would get 3 ions. 1 plus 2 is 3. And you needed a 2 here to balance for charge and to balance for chlorine atom. If you had sodium phosphate, you'd get 3 sodium ion and 1 phosphate ion. Let's say, for example, that I gave you aluminum chlorate. I want to know the value of I. How many ions are released? Aluminum chlorate. Give it a shot. Go ahead, Chase. What'd you get? I got 4 also. Did we all get 4? Mm-hmm. Do you like typing in the things as you go, or are you sort of going back and forth with it?
I liked it at first and then it deleted everything I typed, so I'm kind of going back and forth. No, because it said it downloaded improperly and it had to re-download, so I clicked OK. Well, first I clicked the X.
So
and then
if
it came
I just shoved it up there this morning, but when you opened it, you could have made it a Google Doc, correct?
That's what I did.
I-
And then you
You
could
can
type
open
in
it
it.
in a new tab and then download it.
I think the problem is
All right.
that I tried to keep it as a Word doc.
All right, you'll let me know. I thought of it this morning. I can convert it, but sometimes when it converts, the fonts are like, whoa.
And also, it didn't, like, I kept it as a Word doc though, so some of the formatting was weird.
All right, comfortable with I? All righty. This too is review from the previous chapter. We'll take it to a new level, but I know you'll do really well with it. In this particular problem, this is really not a great problem without a calculator. I'll give you one that is afterward, but I like this one because we essentially live on the ocean. It says seawater is essentially 0.438 molar sodium chloride and 0.512 molar mag chloride. We want to know the concentrations of sodium ion, magnesium ion, and chloride ion in salt water. So what's happening here is we need to figure out the concentration of ion in each salt, and then for the salts that have, if there's a common ion in both salts, we add them together. All that's given are the concentrations. No volumes are specified, so this one's pretty straightforward. From the sodium chloride, we get sodium ion and chloride ion, and the mole ratio of ions to compound, everything's 1 to 1 to 1. So whatever the concentration of chloride ion is the concentration, whatever the concentration of the salt is the concentration of the sodium ion and the chloride ion. Why don't you go get a drink? Go get a drink. You'll feel better. If you have magnesium chloride, that's magnesium ion and chloride ion. How come you have 2 chloride ion for every mag chloride? Because you got to balance for charge. So you have 2 to every one of these. So these 2 concentrations are the same, but the chloride ion is twice what you started with. So you have 1.024. Are you with me? Good. So here, you have this from here, you have the magnesium from here, and to get the chloride ion concentration, you're just going to add these 2 quantities together. And that's your chloride ion
Why
concentration.
do you add them?
You tell me.
Because you multiply it by 2.
Why did you add these 2 together to get chloride ion?
Because they're chloride, because the chlorine is in both compounds.
Yeah, the chloride ion is in both compounds, or the chlorine atom. Yep. So it's in both places, so you got to add them together. So look at this one. This one's just like that one. Let's do it together. It says calculate the concentration of sulfate ion when the following solutions are mixed. Okay. We want to know the concentration of sulfate ion. And for sodium sulfate, the concentration's 0.3 molar. And for the concentration of aluminum sulfate, we've got 0.5 molar. Okay, here's my approach. I have sodium sulfate. I'm going to make ions. The generation of ions is clear. So if this is 0.3 molar, why is the sulfate ion also 0.3 molar? 1-to-1 mole ratio. 1-to-1.
Is it always 1 to 1?
No, because this would be, what would this concentration be? Sodium ion, if asked for it. 0.6, because it's 1-to-2.
Okay.
So if you have aluminum sulfate, you have 2 aluminum, and if this is 0.500 molar, we're only interested in this one, what would that be? What? This would be 1.5? How come? Why would it be 1.5? Why would it be 1.5? Because you multiply this by 3, right?
Yeah.
Okay. So now, how do you get the total concentration of sulfate ion? You add these together, right?
It's not that hard.
Nah, it's pretty easy.
Chill.
No problem? So let's do one a little harder. Here we go. Here we don't go.
It's nitrogen. Next one is nitrogen.
I think you skipped one. We want to do the next example together. It says calculate the concentration of iodide ion when the following solutions are mixed. We've got these. We want iodide. This one's trickier. For those of you running ahead, be careful because the volume is additive. So this one's a little trickier. I'll walk through this one and I'll let you try the next one. So on this one, it says we want to calculate the concentration of iodide ion. For sodium iodide, we have a concentration of 0.300 molar, and the volume of that is 500 mils. The concentration of chromium-3 iodide is 0.2 molar, and the volume is 300 mils. This one's a little different. The first thing we want to remind ourselves of is that concentration expressed as molarity is moles of solute over the total volume of solution in liters, or millimoles of solute over the total volume in milliliters.
So we convert moles to millimoles. Milliliters to
Your easiest approach is to get millimoles of each one, to get moles or millimoles of the ion in question, and then to divide by the total volume of solution. So what you're going after here is millimoles of sodium iodide is equal to the concentration of sodium iodide times the volume in mils. Now, you have to be able to do math without a calculator. And looking at some of the other classes' quizzes, going over a few questions with them, they just couldn't do the math in their head. Easiest approach for me. I'm not sure it'll be for you. We'll find the best approach for you together. I always did this. I hate decimals. I move this one to the right. I move this one to the left. 3 times 50 is? So that's 150 millimoles of sodium iodide. Now from sodium iodide, I get sodium ion and iodide ion. And if this is 150 millimoles, why is the iodide ion also 150? 1-to-1 mole ratio. Good. So this is the first piece of the puzzle. Now on this side, to get the millimoles of chromium-3 iodide, I've got 0.2 molar times 300 mils. And again, moving one to the right, moving one to the left. 30 times 2 is 60. From the equation, I've got chromium-3 ion and 3 iodide ion. If this is 60 millimoles, what's the iodide? 180. Second piece of the puzzle. The concentration of the iodide ion then, you've got 150 plus 180 is 330 millimoles of iodide ion. What's the total volume of solution?
800 milliliters.
800 mils when you add the two together. Now,
Where's the 330 come from?
The 150 and the 180. The iodides.
And then what's the bottom number if you move it?
Where did we get the 800 from?
Plus
The
300.
volumes.
You got it. Adding these two together.
To, do that. Alright, I see it now.
Now, without a calculator, you might have trouble getting the exact answer, but your answers are not going to be that tight. For example, what's 200 over 800? 0.25. It's a quarter. 2/8 is a quarter. What's 400 over 800? A half or 0.5. So you're somewhere between those two, and you're a little closer to the 0.5 than you are the 0.25. This is 0.412 molar. But again, in a multiple choice situation, you would just find the range and you'd be fine. If they gave you 0.25, 0.412, 0.5, you would know what it was. I would like for you to try the problem highlighted in yellow in your notes. Give it a shot. Yeah, guys, watch the food by the Chromebooks, the little potato chips and stuff. That's going to be a mess. No food by the Chromebooks. I don't know, you guys, be careful. You're going to get me in trouble. This is what I got.
Okay. So is that 540 over 900?
Yep. Both of which are divisible by 9.
Seems simple enough. It's not that hard.
Nope. All right, let's learn about some different reaction types. We'll do a little more. We'll take a break. All right, with reaction types, last year in honors, you learned about different classes of reactions, but you only wrote one type of reaction. You always wrote a molecular equation. It turns out that there are many different ways that we can write an equation for a reaction. We can write a molecular equation, and I'll give you an example of that. We can write an ionic equation or a net ionic equation, and rather than going through definitions, let's go through the example. I'm going to rework this example. You can watch as I go. You already have it there for you. Last year, if I told you that lead 2-nitrate reacts with potassium iodide, you would start to write the equation as follows. You would have lead 2-nitrate reacts with potassium iodide. And you would say, okay, we've got two compounds, we've got a double replacement. I'm going to put the insides together and the outsides together, and I would get lead 2 iodide plus potassium nitrate. And you'd be golden. You'd balance it off and you'd be done. I'm not going to balance it at this point. So what you have here is known as a molecular equation. And again, this is in your notes. Molecular equation, where essentially all formulas are written as compounds. Well, you can write an ionic equation. And in an ionic equation, any aqueous substance is split into ions. In your double replacement reactions, one of the products will be a solid. I'll show you how to determine that. In this case, it's lead 2 iodide. All the other ones will be aqueous. And instead of writing them as a unit, we will break them up into ions. We will have lead 2 ion, nitrate ion. Again, I'm not worried about the balancing at this point. Potassium ion, iodide ion, lead 2 iodide. That's the solid. The S will tell me don't touch it. And you'll have potassium ion and nitrate ion. That's an ionic equation. You can also write a net ionic equation, abbreviated as such. The difference between an ionic equation and a net ionic equation is a net ionic equation does not include spectator ions. spectator ions are on both sides of the equation, and they are not directly involved in the generation of the solid product.
So how come for the products, the lead and the iodide are together, or the other two aren't? Oh, solid. Okay, I got you.
Okay? Spectator ions then will cancel. And they're not included in the net ionic equation. And then you do, of course, have to balance it. Spectator ions, hang on. Your spectator ions are not directly involved in the generation of the solid product. And what you will find with your spectator ions is you can always find them in your aqueous product. There were a few questions, and I don't know who was first. Sam?
How do we determine like what's the solid and what are the spectator?
That's going to be based on your solubility rules, which I'll do in just a minute. Or a few minutes. You good? Okay. Let's take a look at precipitation reactions, double replacement reactions in this regard.
The first precipitate will be produced from aqueous silver nitrate and aqueous sodium chloride. Aqueous sodium chloride is added to the silver nitrate solution. We observe a white precipitate of silver chloride. This heavy precipitate thickens and falls to the bottom of the test tube as more aqueous sodium chloride is added to the silver nitrate solution. This is a white precipitate of silver chloride. Again, we take aqueous silver nitrate. This time, we are going to add aqueous sodium iodide. When the sodium iodide is added to the silver nitrate, we get a pale yellow precipitate of silver iodide. Note that this precipitate is not the same color as white silver chloride. It is very pale yellow or cream colored. The cream silver iodide falls to the bottom of the tube and begins to form thick lumps.
This one looks kind of cool.
Watch it, yeah.
Oh, it's very long now.
What I have here is two firmware flags.
Let's get to the good part.
We have some water. Also make it aqueous solution. And both of these. the
No, he
nitrate ion
doesn't.
anode-
That's silly.
Yeah, you say water.
Water.
Looks like orange juice. That's why you never drink anything in the lab. Safety first. We're going to learn how to write net ionic equations. They're very fun, but Sam had a good point. You need to know what is soluble and what isn't. And I'll leave you hanging with that for a few minutes as we take a break, and we'll come back to the second piece, which will be very short in a few minutes. Questions?
You sound like you're going to commercial.
I am going to commercial.